and welcome to the Taiwan Earthquake Reconnaissance Briefing webinar. I'm Shiza Fatima, an EERI intern, and I'm glad that you've been able to join us today for this webinar session. In this event, reconnaissance teams that travel to Taiwan to study the February 6, 2016 earthquake will present their observations. The content will provide key insights into various aspects of shaking characteristics, earthquake damage, response, and performance of pre-mitigation measures. But before that, I will start by going over a few items so you know how to participate in today's event. So right now, you're seeing a screenshot of the attendee control panel. This control panel should appear on the upper right corner of your screen, and it allows you to participate in today's event. This orange button right over here is the open and close your control panel button, so you can use it to open and close your control panel. In the audio pane right over here, you are by default set to the mic and speaker system of your computer. However, I would strongly recommend a hardwired internet connection or a telephone line connection for better quality audio. If you want to listen in through the telephone, please select this telephone option right over here and the dialed-in information will be provided. Here is the questions and answers pane. So the way that it works is that you can submit your questions for any of the panelists through entering the text over here and hitting send. And these questions will be addressed at the end of the session during the question and answer session. All right. With that, I would like to introduce Charles Hike, the chair of EERI's Learning from Earthquakes Committee and the executive vice president of ImageCat to start today's session.
Thank you, Shiza. For those of you that aren't familiar with EERI, I'm just going to be giving a quick overview of the Learning from Earthquakes program so that you guys can understand what we're going to be doing here. So we are a global nonprofit technical membership society with over 3,000 members, chapters throughout the world, dedicated to reducing earthquake risk. And our flagship Learning from Earthquakes program is our reconnaissance efforts that has been going on for over 50 years. We go out after earthquakes and take pictures, collect data, make observations, write reports, give presentations, and like the ones you're about to hear, and so forth, so that we can all concentrate on mitigation and building more resilient communities. So for this event, things were a little, Shiza, can you go ahead and advance the slide? There, oop, no, I think that's too many. Okay, there we go. All right, so for this event, we coordinated things a little bit differently. We served as a coordination effort for the teams that went out. We had over 10 international and U.S. reconnaissance teams that went out and collected data, and we integrated that data into a virtual clearinghouse. I'll show that in just a second. But the teams that went out that will be presenting today are the first three here on this line, and on this table, and the ones that are in bold here are the ones that will be presenting today. So another unique feature of this event is that we collected data from all of the teams that went out and integrated them into this GIS environment, where if you click on these individual points, you're able to bring up photos that were taken on site, as well as the notes that were taken by the folks that took the pictures, so that you can get an idea of the spatial distribution of the damage, what types of facilities were damaged, and so forth, and cross-reference that with the ground motion and liquefaction and other data that might be in the background. So this gives you kind of a spatial distribution of the damage. So we're currently launching this for Japan and Ecuador. And for the Taiwan one, you can go to this site right here and bring up the map and the data, as well as reports that were collected from are put together by the various teams, the presentations that will be given today, and a video recording of this webinar. So in order to put together the virtual clearinghouse, it takes a lot of effort to massage the data into the right format and to launch the GIS and so forth. And That's been spearheaded by our Young Members Committee, and these are the folks that worked on the Taiwan one. We've got additional people that are putting together the Japan and Ecuador one as we speak. And in addition, we'd like to thank the Taiwanese colleagues. If you've ever been on one of these events, you know that it just takes an awful lot of coordination to get access to the various sites, to know where to go, to navigate the earthquake damage and so forth. So we want to thank our colleagues in Taiwan who've helped the teams collect the data that you're going to hear presented on here shortly. So with that, I'd like to hand it over to Kevin Clahan, who will be principal from Lettis Consultants, who will be talking about the geology and seismology.
All right. Good morning. My name is Kevin Clahan, and it's my pleasure to get things started. I'll be summarizing some of the aspects of the geology and seismology of the recent Mainong earthquake. And like several of the following speakers, I participated on the GEER team, Geotechnical Extreme Events Reconnaissance team, that deployed to the earthquake on February 13th, so about a week after it occurred. The Mainong earthquake occurred early in the morning on February 6th. It was a moment magnitude 6.3. It had a moderate depth measured between about 16 kilometers and 23 kilometers by different agencies. The earthquake occurred on a blind fault that produced primarily strike-slip motion with an oblique thrust component. The earthquake appears to have ruptured from an east to west direction, producing a noticeable long period velocity pulse near the city of Tainan that we'll discuss a little bit more under ground response later. In Tainan, more than 20 multi-story buildings were severely damaged by this moderate earthquake, including 11 that suffered complete collapse. And the casualty was extremely high. Most of the casualties occurred in this one collapse of the Weiquan Jinlong complex that is the image on the left of the screen. Approximately 114 of the 116 fatalities occurred in this building. All right, big picture tectonics. The island of Taiwan is the product of both subduction and collision of the Philippine sea plate and the Eurasian plate that's converging at a very high rate of about 82 millimeters per year. It's a bit of a complex tectonic system where you have subduction of the Philippine sea plate in the north, and then you have the opposite sense of subduction in the south of the Eurasian plate beneath the Philippine sea plate along the Manila Trench. We'll talk a little more about that. So collision, Taiwan is a very young island. It's only about 5 million years old when collision began. That collision between the two plates has progressed southward, and so the older part of the island is to the north, and the younger materials that are just becoming subaerial now are towards the south. And so the area that we're going to be focused on is in the southwest part of Taiwan, and that is about the youngest subaerial reach of the active orogeny. All right, this photo shows some of the tectonics of Taiwan, and I want to focus on the southeast part of Taiwan in particular. Again, if we look at this diagram here produced by Bruce Hsu, we have some of the older structures up here. This is post-collision. We have some back arc extension behind the Ryukyu subduction zone. To the north, we have the Manila Trench to the south, where we have incipient collision. There's a large accretionary wedge, which you can see here as a part of a big fold and thrust belt. And then our Mainong earthquake occurred just at the head of the Pingtung Plain. And so we're going to be talking about this area. And just geographically, I want to point out the cities of Tainan and Kaohsiung, two large cities in Taiwan. Most of the damage that we observed was around the city of Tainan. It also had a very high rate this area of the world has a very high rate of geodetic motion on the order of about 50 millimeters per year across numerous structures. And these structures include north-south trending reverse faults and east-west trending strike-slip faults. Some of the historic earthquakes that are notable, since the year 2000, we've had about 12 magnitude 6.0 or greater earthquakes within Taiwan. These have been ranging from relatively shallow to moderate, 12 to 27 kilometers. All of these earthquakes since 2000 have occurred on previously unknown blind faults. And you can't go through Taiwan without mentioning a few of the larger destructive earthquakes. There was the very devastating Hinshu Taichung earthquake that occurred in 1935, and that's located number 9 on the diagram on the left. And then the Chi-Chi earthquake is represented as number 21, that occurred in 1999 with greater than 2,500 casualties. One other earthquake I want to point out, and that we'll be talking about a little more in detail, is the Jishan earthquake, which occurred almost immediately next to, it's about within 10 kilometers east of the Meinong earthquake. And it was very similar in location, size, as well as mechanism. So the focal mechanism solution, again, it's mainly a strike-slip event with an oblique thrust component. The mechanism is consistent amongst many of the agencies, although, as I mentioned before, the depth varies. USGS has it about 23 kilometers versus 16 kilometers for the Taiwan Central Weather Bureau. And then the image to the bottom of the screen here is just, again, to get us oriented with this part of the world. The Meinong earthquake here occurred at the head of the Pingtung Plain, which is a down-dropping alluvial plain. We have the western foothills, which are a fold and thrust belt, which are fairly recent. We'll see a cross-section through there. And then we see the city of Tainan, located near the coast, just to the west of the western foothills. So some of the seismologic aspects, it's believed that the earthquake may have started with a relatively small event, followed by a larger event near the Tainan region. And so it produced a rupture and a velocity pulse moving towards the northwest. The image on the left shows a teleseismic waveform analysis, which shows a secondary S wave or shock about 20 seconds after the initial shock. We suspect that this unidentified event may be related to distinct vertical deformation observed in INSAR data near the town of Guanmiao, and I'll talk about that a little bit later. Again, it's a complicated rupture, and more studies are still being done to better understand the actual fault behavior. So some of the aftershock data, there's 2 clusters of aftershocks. One that's grouped around the main shock with depths between the ranges of 10 to 20 kilometers. And then the other aftershock is located to the west, closer to the city of Tainan, with deeper hypocenters. And again, these aftershock patterns, along with an observed long period velocity pulse, which Dr. Sun will talk about, suggest that there's a complex earthquake mechanism going on. The image itself is showing the plan view, the 2 clusters, and then A, B, and C are profiles indicating the different depths. This is a schematic cross-section, just sort of representing the general geology of that area of the world around Tainan. And so the history of this area can be summarized in 4 different depositional sequences. First, we have the deposition of the Miocene to Pleistocene marine deposits. They make up the western foothills. The western foothills are being uplifted by the constant compression within the area. The subsequent then deposition of the Tainan Formation. The Tainan Formation, again, is a Holocene formation, shallow marine. You'll hear the term Tainan tablelands, and so that more resistant Tainan Formation makes up those higher elevations. We then had a series of marine terraces that were deposited, and then we had finally the deposition of the shallow Taiwan marine estuarian deposits. And this Taiwan formation is important because it's very young. It's less than 3,000 years old, and even historically, parts of the Tainan area were inundated by an estuary. We have very fine sand and silt deposits. Again, they're very thick, so we have a lot of our deformation associated with the Taiwan formation. Again, more on the local geology. The ongoing shortening and associated folding and faulting in the region has produced topographic highs consisting of the more cemented Tainan formation, as well as topographic lows that are filled by the Taiwan estuarian deposits. And the figure on the left here notes this uplifted Tainan formation in yellow and the Taiwan formation here in pink. And those two colors correspond to different liquefaction potential categories. And so they're both in the high to very high categories respectively. Again, evidence for poor performance is evident by the collapse of buildings, damaged structures, etc., and liquefaction primarily occurring within the Taiwan formation. And you can see the symbology here. Red indicates collapsed building, orange is a damaged building, and then purple is areas of liquefaction. One of the things that we look for as part of our reconnaissance, we look for whether or not there's any associated surface deformation or surface fault rupture. And so what we've concluded is that there is no conclusive surface rupture associated with the Mainong earthquake. However, these images of INSAR data, these are ascending and descending images provided by JPL and Caltech, and they provide evidence for uplift of the western foothills as well as an area around the city of Guanmiao, located just to the west. And so the next slide is going to look at this particular image C from the Sentinel data, showing uplift of the western foothills as well as uplift of these hills just to the west of the city of Guanmiao, as well as a striking north-south trending lineament. Uplift during the earthquake, I should mention, is on the order of about 12 centimeters within the western foothills and about 10 centimeters within the Guanmiao hills. So this is an image of that Sentinel data blown up here. And what we're seeing is a very striking north-south trending lineament with uplifted Guanmiao hills to the west and then the western foothills fold and thrust belt to the east. And so this is suggesting we have a west-dipping fault that's controlling some of that deformation. This fault was previously unrecognized. We're calling it the Guanmiao fault. The Longshun fault, which is located along the eastern margin of the western foothills, was previously known and is well described and has excellent geomorphology. So whenever we see a new fault, we get very excited. And so a lot of our, couple days of our reconnaissance was exploring this relatively new or previously unrecognized feature. And what we found is that there is a very sharp escarpment, east-facing escarpment. Again, we're looking at a west-dipping thrust fault, which may have been activated by the Mainong earthquake. And that's, again, why we may have some more deformation in the Tainan area than we see in the main shock area. The hills to the west of the Guanmiao fault are tightly folded, north-south trending anticlines and synclines. This strong geomorphic lineament is aligned very nicely with the lineament that's shown on the INSAR data. And so one of the activities that we did is we flew drones or UAV and made it UAV imagery and created DEMs to show us the actual fault trace. And so this is about a 4-kilometer long stretch of the new Guanmiao fault, which is showing a relatively linear escarpment. And so that was kind of that sums up some of the more important geologic aspects. I want to pass it on now to Dr. Sun. Joseph Sun will be summarizing the ground response and some of the liquefaction effects. Thank you.
Thanks for hearing you.
I'm sorry. This is Joseph Sun. I muted my phone. I'm an engineer with Pacific Gas and Electric Company. I will be presenting the geotechnical aspect of this reconnaissance on behalf of GEER. I will be talking about ground motions, liquefaction, slope, dams, and lifelines. And this is only a small portion of what we observed. I encourage everybody to go to the GEER website and download the full report. This slide is the recorded PGA and PGV of the earthquake. As you can tell, all the little dots are seismic stations. Around the Tainan area, this corner is Tainan. Around the Tainan area, the maximum recorded PGA roughly is about 0.25 G. Near the epicenter, the recorded PGA is roughly about 0.4 G. The peak ground velocity, on the contrary, is in the Tainan area is roughly about 50 to 80 centimeters. If you are a seismologist, this ratio between the PGV and PGA is somewhat off. For the peak ground acceleration to generate this kind of high velocity, the peak ground acceleration should be around 0.5 to 0.8 G. As Kevin just mentioned, before this earthquake in 2010, there was an earthquake called Jianshan earthquake, have the similar magnitude, similar epicenter, similar focal mechanism. However, it generated a PGA that is much less than the Meinong earthquake. The comparison of these two may be of interest for future researchers. This is a station list of all the PGA recorded at the site. As you can tell, near the epicenter, the peak ground acceleration is about 4 G, and toward the western end of the deposits, Merino deposit, it's about 0.25 G. I want to point it out on this plot in observation. You can see that this station list shows two numbers. One on the left is the PGA in the east-west direction. The number on the right is north-south direction. As you can see in the Tainan area, the east-west is much higher than the north-south. And this can also be seen from near the epicenter. This A730, I'm going to be showing later on, shows also a high east-west component than the north-south. Does this thing have anything to do with the damage potential? We will be hearing more about it later. This is the ground response recorded at station 730. It is a rock site, as you can tell from the pi spectral response at about 0.2 seconds. The duration is very, very short. It's about 8 seconds, which is about the right duration for magnitude 6.3 earthquake. But what I want to point your attention to is near the 0.5 to 0.7 seconds, there is a pulse, predominantly in the east-west. Could this be related to what Kevin was mentioning, this velocity pulse? We don't know, but we have a strong suspicion it may be. As we move toward the west, we'll be going to a site is in the foothills. The velocity VS30 will be 200 meters per second, about say 600 to 650 feet per second. One thing observed is that in the time history, instead of 8 seconds, look how long extended is. Extended probably to 15 seconds. And you also have the strong velocity pulse at about 0.5 to 0.6 seconds. And also the east-west, the red, is much higher than the blue line. Whether this surface wave has anything to do with a low SPT value at the surface, it is yet to be seen. This is the station at Tainan. Tainan actually is where the mostly heavy damage area occurred. If you notice again, the duration changed from 15 probably to 20 seconds. This is extraordinarily long for a magnitude 6.3 earthquake. This probably doesn't have much to do with the structural response, but it will have a lot to do with the liquefaction potentials because you have a lot of stress reversals during this duration. The other thing I want to point out is that at 1 second period, the structural response has a peak, again in the east-west red direction, much higher than the blue direction, the north-south. You can also see on the time history, there is a very strong long period duration that is representing this peak right here. Does this peak and this structural response at closer to 10.8 to 1 seconds have anything to do with the collapsed building? It will be discussed more in detail later. This is basically a summary of all the plots of the substation of all the stations. A730 is near the epicenter. It's on rock. As you move toward the west, you see that the east-west, the red is always higher than the blue, the north-south. As you go to the shoreline of Tainan, again, this is the predominant period that we are seeing. Let's talk about liquefaction. Liquefaction for a geotechnical engineer, it's what we live and die for. So the question asked after this earthquake, what have you learned from the earthquake regarding liquefaction? Can a 6.3 earthquake really generate that much liquefaction at sites that are located 35 miles away from the epicenter? When I first got this news, that's what first came into my mind. And then I realized Loma Prieta, a magnitude 6.9 earthquake, caused significant liquefaction in San Francisco, which is about 70 kilometers from the epicenter. So the key thing is that the material must have a lot to do with this observation. Does liquefied soil have any unique characteristics? We later find out no, it's just a typical sand. It's just deposited very, very loosely. What opportunity presented by this earthquake, which is a 6.3, that Chi-Chi cannot produce? This is important for us to know that with a smaller magnitude earthquake, you'll be able to identify the weakest area of your area. So this is really a good opportunity. Whereas magnitude 7.3, when it hits Tainan, everything will be wiped out. So you will not be able to find out the weakest zone. Other than PG&E duration, are there anything important secondary factor that contribute to liquefaction? The answer is no. And yes, the yes part, meaning that we shouldn't characterize liquefaction size based on geological description only. We found out a lot of man-made fill caused liquefaction. What is common about this earthquake and New Zealand crisis earthquake? One thing important is that the myth of geotechnical engineer thinks that it's not related. Earthquake can densify material, such that it will not liquefy in the future. It ain't true. Now, we have repeat liquefaction at the sites. Other than a few tilted photos of repeated photo of tilted house, why do most of the structure system perform well in liquefied area? This is a topic that Professor Hutchinson will be describing later. Why does the sand is more often observed along the edge of the building rather than free field? We don't have a lot of free field site liquefaction. This is, I think, is regarding potentially rocking of the buildings that are on top of a marginally liquefiable soil. I will be talking about only the one free field liquefaction later on. The last thing is important for the local folks. Are there any screening tools that can be used to identify liquefiable material? And I think we do. So this is a plot by Abraxas, plotting the epicentral distance versus magnitude. And you can see the red dot, red are the boundary of the line that separates liquefaction and non-liquefaction. So this magnitude and this distance can generate liquefaction if the material is soft. The gradation shows that the material that liquefied is agreement with most of the historical observation of liquefiable sands. This is the part that says there are a lot of areas that did not liquefy, either from the Chi-Chi earthquake or from the Jiaquan earthquake. This is because the P1 acceleration is low. But since we have the material property, we can probably calibrate the liquefaction curves near the lower end. This is the free field site. This is in Xinhua, and we have seen the sand cones. But what interesting is that if you, from this photo, you can see you have to see the sharp crest and the different colors. So I suspect this area, this location, has been liquefied by aftershocks. I forgot to mention this Xinhua site actually has liquefied before in a previous Jiaxian earthquake. This is the sand that you can see I pick out from the sand boil. It has a lot of clays in it, and at Xinhua site, the blow count is very, very low, usually between 2 and 5. So repeat liquefaction will occur if the material is really soft. Lateral spreading, we have observed 3 sites. I will go relatively fast on this one. The lateral spread push out from the toe, some things from 28 to 50 to 60 meters. That's a far distance to push out. And when we went to the site, we do see that you do have soil that is moist along the toe, meaning that area that liquefied, you do have water. You need to have water to have liquefaction. This is a photo of showing spread number 2 and number 3. Notice that how far the toe was pushed out. This is a photo at the toe. I want to show how level it is at the toe area. And the reason it has liquefaction is because below the liquefiable sand, you have a silty clay layer near the base of the liquefied zone that prohibits water from infiltrating, and this has caused the sand to liquefy at the base of the slope. And this is how they retrofitted the slope. As you can see, they just dump it and didn't compact it. So will this area liquefy again? I'm pretty sure it will. Failure of a Nanbao site is a failure of a golf course. There's no liquefaction involved, other than it is a failure along a cut fill slope. The important thing of this thing is that this will be a case history for us to calibrate the Newmark sliding block analysis. You see, it's almost moving like a rigid block, so it's a good calibration for Newmark sliding block analysis. I want to talk about dam performances. There were a lot of them that were shaken by this earthquake, including the tallest dam in Taiwan, Jiun-Wei Dam, which is 134 meters. The crest of the dam had been shaken to 261 gales, or 0.25 Gs. And the other one is a tall one, is 88-meter die Nanhua Dam. This is a curved axis embankment dam. The top of the dam recorded a peak ground acceleration about 0.3 G. I want to also mention another dam called Wushan Tou Dam. This is a hydraulic fill dam. The top of the crest recorded 0.18 G or 0.17 G. This confirms that liquefiable hydraulic fill sand can sustain performance up to 0.2 G, as was observed by Harry Seed by looking at the 1906 earthquake. So all these 3 tall dams, including a hydraulic fill dam, performed well. The Hutchinson is the only dam that suffered damage. I will bypass this one. The Hutchinson is an old dam, 30 meters high, but has some damage occurring along the edge of this corner. No major damage, but if you have a dam that has a corner, there's some stress concentration there, and that's what caused the damage. Lastly, I want to talk about lifeline damage. There were a lot of lifeline damage. Remember that I mentioned that the peak ground velocity is very high. So the water supply line, we have about 400,000 customers impacted. There were 4 transmission line segments that suffered major damage. These are transmission lines over 2,000 millimeters. But all the damage occurred at joints. The collapse of Weiguan building on top of a pipeline, key pipeline, prevents the water repair work being done. And that caused the total delay of 14 days to completely restore the water surface. One conclusion made by the water agency is that these kind of damage was caused by high peak ground velocity. There were no ground displacement involved in all the transmission line segment damages. Gas supply is limited damage because most of the folks in Taiwan still use propane gas. The damaged pipeline, the damaged water gas supply always was restored within 24 hours. Electricity, about 170,000 customers was impacted. Most of them are from the tripping of the transmission transmission line. In other words, the conductors flap against each other and cause the circuit to short. So it was very fast to restore those, and most of the services were restored within 24 hours. The final 200 and 400 customers not restored it is because building damage. A major fossil plant, Xingda, was tripped. The nuclear power plant in southern part of Taiwan at the tip recorded 0.2 Gs, and there was no tripping, and the nuclear power plant continued operation. With this, I will pass on to Tara Hutchinson, which will be talking about liquefaction-induced building damages. Go ahead.
So my name is Tara Hutchinson, and I'm on the faculty here in the Department of Structural Engineering at UC San Diego. And during this, what I've been allotted is 15 minutes in this presentation. I'll try to discuss liquefaction-induced damage on buildings, and also provide a short overview of the GEER team's effort to contribute to use of remote sensing tools during their reconnaissance. As Joseph mentioned, liquefaction was observed at several locations during this event. And during his talk, he spoke about repeated open fields where surface manifestation, not necessarily obstructed by man-made structures, but nonetheless very interesting and important case histories. He also spoke of liquefaction-induced triggering and lateral spreading problems along riverbanks, namely the Rixey levee. You saw some discussion of that, and what we'll focus on in this time frame is residential areas where ground liquefaction occurred in maturely developed sectors of the city of Tainan. So we'll talk in particular about the impact on three key districts, namely Anan, Jinshi, and Wenhe. The building characteristics and types are relatively similar within these districts, though their vintage varies. The structures in these districts, like many in South Taiwan, range in height from about 2 to 4 stories or so. So low to low rise, I would say, in nature. They're either of concrete or masonry block type construction. Typically, they have an open front and rear or side cover patio, and often we found an add-on single-story carport or other smaller single-story additions that the residents had made provisions for. Importantly, in each of these areas, visible widespread evidence of localized liquefaction features, surface features such as boils and surface ejecta and cracked pavements, gave us hints of the ensuing potential impact onto the community in these areas. So this is a liquefaction map. Joseph showed this also. I provided only for point of reference to South Taiwan, and to set our discussion in context, he spoke about Jiun-Wei and the open field, free field liquefaction evidence and case history there. We'll focus on the outlying areas of Wenhe, Anan, and Jinshi, as I mentioned. We won't cover each of them in particularly extensive detail due to limited time, but rather we'll try to draw from what lessons one can learn from these residential regions with regard to liquefaction impact on buildings. Importantly, one needs to understand the characteristics of the soils at the site, and the most effective way to do that after an earthquake is to take samples of ejecta from the sites. And so NCKU, courtesy of Professor Chang and his students, sampled these soils while we were on site, conducted index tests, and found that the materials are predominantly of poorly graded fine sands and silty fine sands with fine contents ranging from 6 to 30%. Grain size distribution curves support the poorly graded nature of the soils with a uniform gradation with C sub U values ranging between 1 and 3. Shear wave velocity profiles were also conducted by NCKU using MASW immediately after the earthquake, And using those shear wave velocity profiles, one can perform a liquefaction triggering analysis. So the plots on the left show the profile, and the plots on the right show the triggering analysis, and reveal that the critical layers rest somewhere between 2 and 6 meters below the ground surface. This is a margin of safety against liquefaction. So we can see that 2 to 6 meter range is important. In the Jiun-Wei district, there's a question whether or not there may be some deeper pockets extending potentially 8 to 10 meters below the ground surface. So considering the soils of the site and using liquefaction triggering methods, why then are these regions not mapped within zones of high liquefaction potential? They're in fact on green or yellow mapped regions. So one needs to develop an appreciation for the local site history, and we learned quite a lot about the regional growth. In South Taiwan, many residential regions, in fact, during the 1970s and 80s, saw rapid economic growth during that period and development. So as this growth was occurring, regions previously used for farming and fish ponds were quickly backfilled and used to build communities. The backfill occurred at different times and with different developers, and likely using different construction means and materials. As a result, seismic performance of individual backfilled ponds then will vary. And more importantly, the reduced quality of the backfill in the ponds in these residential areas is likely responsible for the liquefaction potential in the local pockets that ensued. We can set this in context by looking at historical features of the region. We show here a previous old map of the Annan district, and locals identified for us an old dike which previously encapsulated a pond and was then backfilled and developed. The liquefied zone is shown in dark red here, and as you can see, it rests right within the feature of the old dike. Most significant surface features providing evidence of liquefaction and the heaviest damaged buildings rested within this red zone. Others were scattered within the dike boundaries as well. If we zoom into this region using an aerial image taken via UAV, we can start to understand the damage features as we walk through the communities here. But to understand how we characterize this, it's important to provide a link between ground failure and structural damage as an indicator of performance. So for this reconnaissance, we drew from the work of Bray and Stewart following the 1999 Koscielny earthquake in Turkey. They advanced the concept of linking ground failure and structural damage indices by using to help characterize damage patterns emerging in the Adapazari region. They categorized local ground feature failure using a three-step gradation ranging from none to minor GF0 and GF1 to significant as a GF3 categorization. And those within the GF3 index were set to a situation where one observed more than 25 centimeters of settlement or greater than 3 degrees of tilt, or lateral movement greater than 25 centimeters. Equally important is the other leg of the stool, the manifested structural damage features. So adapting some earlier work of Coburn and Spence, they graded damage from no observable damage with an indice of D0 up to, and in linearly increasing in intensity, damage state of collapse assigned about an indice of D5. So adapting this concept, let's take it to the Annan area. This map is useful as it provides context to the extent of ground failure as contextualized with foundation damage and its link with physical damage state of buildings in the region. So we'll just spend a little bit of time on this map. To interpret the data here, we have to discuss the mapping strategy. In this case, ground failure is delineated by a color coding on the border of the individual building. So each of these borders color codes for us the intensity of ground failure, blue being a cool or no damage, and red being the most extreme damage condition of ground failure. To characterize structural damage, we use the fill color of the boundary of the building. So again, no, blue used for a cool or a no observed visible structural damage, and spanning to a red or most intense collapse state of damage. Several important aspects can be discussed in the context of this map. If we begin with the highly dominated blue shading at the exterior buildings, these are graded between a D0 and a D1, so structural damage of none to very minor cosmetic, yet they have ground failure features of a 1, so there's some minor ground failure features observed. In contrast, one asks what sets these buildings apart from the interior structures, which observed moderate to severe ground failure and corresponding moderate to severe structural damage. The boundary buildings, in fact, have a positive continuity of their structural foundations and a continuous elevation and continuous build pattern. In other words, the foundations were not added on, or no appendages and the like were observed in any of these surrounding buildings. Structures within the interior with visible significant structural damage graded as yellow through red, red, for example, here and here, and yellow color-coded damage here, were mostly associated with structural discontinuities, primarily stemming from those discontinuities at the foundation, and often associated with lightweight single-story addition regions. As we'll see in just a minute, we'll look at a few vantage points walking into this alleyway, looking at a moderate damage situation, and looking at the backside for comparison. This pair of photos is one of those vantage points, articulates the nominal ground failure graded as GF1, where settlement of the structure is observed. You can see the manifestation of perimeter settlement in ground feature, which we categorized as GF1 here. The damage to the structure, however, was only cosmetic in nature, graded as a D1 in this case, despite the manifestation of the settlement. There is certainly a lack of significant structural damage, likely due to the well-connected and continuous foundations of this building. Here now is a view from the southeast region of that last mapped image, looking into several buildings where clear evidence of liquefaction in the field is noted by bulging of the exterior slabs, and evidence of rotation of screen fences and surface boils and the like. The pair of buildings on the left of this image observed ground failure features at their exterior classified as moderate to severe, GF2 to GF3, while the resulting structural damage was graded as heavy. You can't see it from this viewpoint, but each of these has significant discontinuities and structural damage of their supporting structural elements at the base as viewed from the inside of this alleyway. In stark contrast, the long building on the right, likely of similar unit lineal weight, let's say, in terms of just scanning at their elevation, and surrounding ground failure characteristics just adjacent to them. Nonetheless, the ground failure right adjacent to the building we classified as minor, and ensuing only minor cosmetic structural damage was observed. Its foundation and structural system was highly continuous, and no exterior single-story additions were observed along the features of this particular building on the right. So you see it's got a blue interior and green perimeter color coding associated with GF1 and D1 respectively. The final sequence of images articulates severe ground failure and corresponding structural collapse. This alleyway, this was the view at the top of that mapped view that we looked at 2 slides ago. This alleyway shows, though narrow, gives us a perspective of a number of important features. To the left of this image is an excessively tilting and settling building, and within the middle is a single-story high bay addition. You can see it distorted here. It's attached to a 3-story structure in the background here on the right, which suffered excessive settlement on the order of more than 30 centimeters. The lightweight single-story rear structure, which shows significant distortion, as it must attempt to carry the large shear strains that are induced during the collapse of the building it's attached to the right. To gain a perspective of this scene, we captured a suite of LiDAR scans at this location. And here I want to try to play a movie and fly you through a sequence of this LiDAR model. So we tested this yesterday, and let's hope it works just fine. You're seeing just a bit of noise as we fly into the LiDAR model. You can see the point cloud that's been generated. We're very happy that we were able to embed these movies within the GEER report, actually. So you can download this now. You can go through. It's called the On Fly, and it's linked within our report. You're now flying through the interior. You can see the features of hardscape damage. You can see the low-rise building in the front of us, attachment, and now you can turn. This just happens to be we're manipulating this particular model. I'll show you in a minute. How we can go in and manipulate models on our own as well with another example. Okay. This last view is just looking back. That's the final view we saw in the fly-through perspective as we exited through the alleyway, but it does give you a very good picture of the disconnect now with the hardscape due to the excessive settlement and tilt of this building, which was previously on the left of this image here. Similar examples from other regions, and we mentioned at the beginning 3 distinct regions, Jiun-Wei being another. You see the perspective view of a tall 3-story residential building. And in each of these cases, hints of structural damage in the background due to significant relative displacement of isolated footing elements that support, in this case, carports, exterior carports, and hardscapes within those carports. You can see the manifestation of large strains induced on the lightweight components of these buildings due to the surrounding ground failure. Wenhee Street, just to show you a third example, I mentioned 3 on the map earlier, similar issues observed. Now, though, this is an interesting complexity added into the perspective. The image on the left here shows a highly varying geometric feature and discontinuity of structural load path. It's a little bit difficult to see it again. These are very tightly spaced buildings, but let me try to explain. You're looking at an elevation in the roadway feature. The roadway is running to the left and the right here. So it's a very long building in this axis following the arrows here. However, it's got a 2.5-story heavily loaded region at the front near the street side with a 1.5 story exterior, not shown though in the right side of this image. If we take a view behind this building, we can see what occurred due to the liquefaction induced ground failure at the front side of the heavily loaded damage. We can see that a large separation between the 2 buildings developed due to the shear strain that needed to develop or needed to be carried as the building moved to the left of this image. So again, seemingly an addition, but a large, heavy discontinuity, geometric and weight discontinuity promulgating into structural damage. So just my final very short topic, as Kevin showed in his opening slide, and if you looked at the newspaper today, the digital newspaper, and you're tracking what's happening in Japan, we can continue to see the powerful opportunities of remote sensing. This UAV generated aerial model of the collapse of the Weiquan Jinglong complex created by the Department of Geomatics at NCKU was extremely important immediately after the earthquake, particularly due to the humanitarian efforts needed for this event, for this site. These tools are certainly becoming more readily viable. In fact, tomorrow GEER is going to be hosting a webinar led by Dr. Kevin Franke and Dimitrios Zekos on this exact subject for those that are interested. So I imagine that's going to be quite an interesting opportunity for all of us to see a culmination of various opportunities with remote sensing. We too, as I alluded to by sharing with you just one example so far, attempted to bring remote sensing tools to the site and contribute to advancing, rapidly our ability to learn after an earthquake. We brought LiDAR, as you saw from the one model represented. We have many more. We also brought a UAV out to 12 sites during the ground reconnaissance. We collected more than 22 gigabytes of data, 3,200 UAV-generated high-resolution images, and 39 distinct LiDAR scans. We're very proud that we immediately were able to release a report with embedded movies and embedded 3D interactive models. And I can show you just one here. This particular model, I'm going to try to interact with it. This is embedded our report. Obviously, you can maneuver in any direction, zoom in and out of the features, and as well, it's geo-reference, so it provides quite a powerful tool for future analysis. Oops. To my final slide. Okay, so in a last conclusion about the main topic of this discussion was regarding liquefaction-induced building damage. We know that where liquefaction will occur will be largely unknown given prior ground characteristic uncertainty. The historical significance of pond features in this particular event emerged for the Taiwanese community. As a result, residential buildings lacking well-connected foundations suffered most significantly. Well-connected foundations, on the other hand, demonstrated very good performance. So we did see many of these modern grade beam designs, and we know now the importance of this positive continuity in building construction. Since I'm the last GEER speaker, I have just an acknowledgement slide for our colleagues. As Charlie mentioned in the beginning, always having colleagues abroad, and our steering committee here. I want to thank them for supporting the GEER team and providing us the guidance. And then, of course, our local U.S. members, was a pleasure to work with them, and our Taiwanese GEER members as well. And with that, I'd like to introduce Jiun-Wei Lai. He's a designer at Degenkolb Engineers, was a member of the team that visited buildings and evaluated their response during this event.
All right, thank you, Professor Hutchinson. So previous presenters have already talked about the geology and seismology background of the earthquake, and also the ground damage and liquefaction damages during this earthquake. So I'm going to talk about the building response, just briefly talk about it. And I'm representing the Degenkolb engineer team. And our team members include Daniel Zapata, Kirk Johnston, In-Sung Kim, and Gary Hagen. So this slides just briefly give you an idea about the statistics of this earthquake. And because we are focusing on the building response, I'm just going to talk about that after this earthquake, more than 5,000 building structure reported damaged, and 247 red tag and 335 buildings yellow tag. And remember, these numbers are not the final numbers, and the final numbers should be higher. So this slide just gives you a general idea about the building code in Taiwan regarding the design of reinforced concrete structures, because most of the damaged structure we observed during this trip, they are the reinforced concrete structures, and most of them, the damaged structures actually designed before 1991. Which most of the design code in Taiwan, they are based on the ACI 318 code. And we also going to talk about the design base shear force in Taiwan. And these just briefly shows the evolution of the design base shear. And most of the damaged building we observed, they pretty much designed by the 1982 or before. So using the formula very similar to the UBC code, and depends on the time period they designed, the base shear could be between 5% to 23% of the seismic effective weight. So previous speakers have already talked about the ground motion characteristics, and I just kind of want to review that this response spectrum actually recorded during the earthquake within the Tainan region, which close to many of the damaged building. And you can clearly see that the east-west component is higher than the north-south component. And there's a significant peak around the period about 1 second. And at this, we found 3 damaged buildings. They have fundamental period very close to 1 second. So here, just want to show you some pictures about the typical construction type in Taiwan. And you can clearly see that they have like a mixed use, reinforced concrete, low rise or mid rise. They have retail stores at the first story and residential above. And they also have more modern high rise, which are composite constructions. So we have visited 19 sites during this trip. And today I'm just going to talk about 9 buildings we visited. So the first building I'm going to talk about is Wangling Hotel. It's a 10-story building. If you look at the left-hand side pictures, you'll see that clearly it has a tall lobby issue, and it's a vertical irregularity. And it's designed in 1996, but abandoned for around 10 years, and they kind of want to renovate this building to do for hotel use, but they didn't survive this earthquake. So 4-story collapse below the fifth floor and above. If you can see the right-hand side pictures. And if we go back to the back side of the building, and the red box here shows the staircase. And look at the detail of their structural detail. It's clearly a non-ductile detail, as we typically see in the field. So the next building we are going to talk about is the Xinfu building. The left-hand side shows the before earthquake. The right-hand side shows after earthquake. And it was a 7-story building. And during the earthquake, the bottom 3-story collapsed. And this structure has a combination of plan irregularity and also the vertical irregularity. So when we were there, the building, they start to demolish the building, but we saw some of the components, structural components took down from the structure, and we can see the tin can. And according to the local engineer, that they mentioned that this tin can is not for structural use, but they just put right next to the structural columns. And we also found that they took the concrete core to do further investigation, if you can see the right-hand side pictures. So the next building, which is the major casualties occurred in this site, the left-hand side shows the plan view of the building. It contains a 9-unit residential complex. And during the earthquake, it is collapsing to the east side of the of the building. And the right-hand side just shows the Google Street View at the viewing from the east side of the building. And you can see that there's like a cantilever portion at the bottom floor, and fewer columns supporting the upper structure. So if we look at the another view after the earthquake, this is the building that collapsed, and we can see that most of the unit from A to G, they are actually crushed. So most of the people survive. They are in either in unit H or unit I, which is the top portion of the structure. So this slide shows the map view of the sites. Just give you an idea that remember I showed the response spectrum, that the east-west component is higher than the north-south. Around the structural period region is about 2 times bigger than the north-south component. So one of the local engineer helping demolishing the building after earthquake, he did a quick analysis of the building based on limited informations and drawings, or using the Google's Street View to construct a model to do a quick analysis. And from the drawings he got, he found that there's some modifications between the original drawings and the as-built drawings. So basically, a couple of walls actually not constructed. And if you look at the model that shows in this slide, the left-hand side represent the original drawings. If you look at the bottom left corner, you'll see some structural walls below the fourth story. But the right-hand side, which is the as-built drawing, you couldn't see those walls. So from the pictures actually took after the earthquake, before they completely demolished those buildings, we can see that at the tension side, you'll see the rebar failure, like either necking or the coupler, rebar coupler failure. And this structure, we think that is a combination of vertical and plane irregularity, and also torsion effect, and lack of system redundancy issues that caused this collapse. And the next building we went was Kingstown Bank. It's an 11-story building, and the left-hand side shows the Google Street View. And again, you can see the tall lobby, and you only have 2 columns supporting the cantilever portion of the building. And during the earthquake, it collapsed to the front side of the building, and also damaged the buildings next to it. So the back side of the building, you can see which is the tension side of the building during collapsing, and you'll see some failure here. And the detail for the transverse rebar is 90 degree, for example, as shown in this picture. So another marketplace building we visited is a 4-story building, and it has similar irregularities, and it has weak story problems. So one of the junior high school we visited, this one is actually they kind of passing the school evaluation program, but the evaluation result is right at the margin. And it didn't collapse during this earthquake, but it has severe damage. You can see that the short column failure and some expansion joints, non-structural wall failure. So as I mentioned before, that most of the damage that is related to the stronger component directions. And at this side, if you look at the blue square, those are the columns that align in the east-west direction, and because they are aligned with the stronger motion direction. So most of them have severe diagonal crack next to the windows. So one of the city hall type office building we visited is a Sansan district office. It's a 3-story building, and from this picture, the overview of the site, it looks like it's not damaged, severely damaged. But if we go inside the building, you clearly can see the short column failure, and it also the failure column, they also align in the east-west direction mostly. So we have talked about a lot of damaged structures. So I'm going to talk about some successful stories. This building is a Grayland district office, and it performs really well during the earthquake. And it was retrofitted, adding 4 shear wall in the system. And if you look at these pictures, actually is the green portion at the front. And if we look at the plan view, which is very similar to the Sansan district office, and this one add 4 shear wall, which is shown on this picture with the red solid lines, and it just simply adding 4 shear walls, and it performs really well. So this is a great the Degenkolb High School. It's also retrofitted, and it performs really well too. And this plan view shows the summary of the retrofit scheme they use for different buildings on this campus. Basically, they add the shear walls, or add the wing walls, or add the brace frame, or add the steel columns at the below the cantilever portion, or they add a steel plate outside the masonry wall. For example, these 2 pictures shows the left-hand side shows they add steel plates on the masonry wall, and the right-hand side shows the rebar layer outside the masonry wall. And they also have other different, the retrofit scheme as shown here, either enlarge the sections or add in the wing walls. And as I mentioned before, in Taiwan, they have a school building seismic program, and more than 400 school buildings were evaluated before the earthquake. And this program is majorly triggered by the GG earthquake in 1999. And after this earthquake, only one building damaged out of 334 that's safe building they evaluated, so which is kind of successful per se. And that damaged building is the building the school building I just mentioned, the Eugene building. But that building, the evaluation report is right at the margin. So with that, I'm going to talk about some final thoughts from our teams. So during this trip, we saw a lot of textbook type failures, but most of the damaged building they have either plan or vertical irregularities, which cause soft story, weak story, and torsional issues. And we also found that some buildings, they have not many columns to support or to back up the system, so kind of a redundancy issue. And also the lack of ductile details, and maybe the construction quality issues. And we saw a lot of buildings like this type in Tainan region, and they're really close to the damaged building site, and they just performs really well. And one of our members said, "Oh, it's just a mystery of nature." And we found that this maybe contribute to the to the side effect, or either the ground motion hit the building in a strong way, or some other variations maybe contribute to these this kind of phenomenon. And so remember I talked about that one of the 10-story Wanling Hotel actually survived in the 2010 Jiaxing earthquake, but it unfortunately it didn't survive the earthquake this year. And one thing we found that maybe some buildings they survive under a particular earthquake is because the earthquake is not stronger enough. So if you have stronger earthquake, those vulnerable buildings may, they still there, and they could be damaged in the future. So one of the major takeaway from this trip is that those vulnerable buildings are there, and we at least need to do something on them, either upgrade them or do evaluation to prepare for the future earthquake. So with that, I'm going to pass the presentation to the next speaker, Kevin Moore, principal of Simpson, Gompers, and Hager at San Francisco, and he's going to talk about the infrastructure response in a resiliency context. Thank you.
Okay.
There you go.
I'm going to try my best to make up some time here. We've only got about 10 minutes or so. So I am Kevin Moore, principal of Simpson, Gompers, and Hager, structural engineering firm in San Francisco, and our group also spent quite a bit of time pursuing buildings, but we saw other things while we were in Taiwan and wanted to share a different type of thought related to the damage observed and how the community responded, the community being Taiwan and even the country in general. So you've seen this before. Some of the key components associated with the earthquake, of course, are important. Also, initial financial costs really don't focus on the actual precision of the numbers here, but the relative costs are very, very low compared to other earthquakes that we've seen associated with a magnitude 6.4, and especially in a large or an urban population. Obviously, here's where the earthquake is located, as you knew before, and what we're going to do is focus on that little area there. And here's a little map indicating the locations of major damage. And you can see it's very widespread, and that widespread damage, of course, indicates that you had reasonable amounts of shaking, not just around Tainan City, but even outlying areas. And we did see building damage as far as point 11 and 10 up there in the far left-hand corner, and a series of damaged buildings a little bit closer to the epicenter there to the right of the slide. So that little red oval indicates the area identified within this photograph. Shangri-La, which is a central hotel location there in downtown Tainan, and the National Chengkang University, where we had quite a few assistants, if you will, and definitely colleagues that were interested in what we were doing, and of course were phenomenally integral in our efforts to actually look at damage and understand what was going on in Tainan. What's nice is that this photograph was taken from a public location far before the earthquake occurred, and it would be safe to assume, and it was accurate, that it looks exactly the same as it does in this photograph today and did prior, and this will come into play when we compare to damage from previous earthquakes. One thing of note, based on the information that was provided by our earlier speakers, is that some buildings have some system issues. Some of that is related to the way that the organizations, whether it be planning jurisdictions or government, look at buildings and provide for zoning. And so there's a need for public space in the front of the building, and obviously creating some corner entrances that might affect those systems. So case in point is one of these buildings that collapsed that was shown before, and you can see that that setback allows for pedestrian throughput, and obviously the access to the lower floors. And as you can see here, another issue that's of note is this is taken during the day. It seems like a relatively normal day, which I assume it is, and not a whole bunch of people here. The traffic is relatively low, and that's pretty consistent with what we saw after the earthquake. Here we were watching the demolition of that same building, and you can see that there's actually more people in this photograph than there was in the Google photograph. So it's the first indication that things were back to normal, other than the disruption of this road that you can see here projecting off to the left here in front of these gentlemen on the moped. We also saw that life was normal. We had some, very nice cars parked around, and obviously it was being used immediately after the earthquake. So most of the people in and around, and this is just behind where I took that previous photograph, where we have actual normal activity occurring directly related in terms of proximal location to the demolished building. This is just an indication of how the residential construction works from a societal standpoint. A residential building is owned by each individual, and you can see here there's 3 openings that are there at the first floor, and of course carry all the way up. My understanding is that Taiwan nature is that you actually own that building for this entire space through, in essence, this slice of what we would consider to be a singular building. And so each individual that owns these spaces then deals with their internal space as they see fit, just like we would an individual home in the United States or in other locations. And as such, sometimes they actually collaborate or own multiple areas, if you will, and develop extensions of original construction. So the original construction was this 3-story, very, very common building in Taiwan with another portion framed up above to allow either use of the rooftop or to give more living space. So just something to keep in mind. This is a shot of some typical damage with inside a residential space. So you can see it's just some cracking of some unreinforced brick that's there. And this is a photograph of the repair that was in progress. We were there approximately 10 days after the earthquake. And that unreinforced brick is being replaced with unreinforced brick. So societal response is just to get their living space back fully functional without any regard to actual building performance. It was a little bit different than what we do here in the United States and in other locations. There was a discussion about the district offices. The district offices generally represent City Hall or governmental type buildings, and the comparison between those district offices are actually nice. There's a general consistency in plan and design between those buildings. You can see as here they're juxtaposed with a retrofit building and a non-retrofit building. They're all part of what is called a public building retrofit program, which is actually associated with some legislation that was passed after the Chi-Chi earthquake. That was the Taiwan Disaster Prevention and Relief Act. And as part of that work, over 27,000 buildings have been inspected, meaning that the government is aware of their condition and can do something about it. And of those 27,000, the government has retrofitted over 4,500 buildings. We talked a little bit about this major collapse, which got quite a bit of press internationally and locally. And you can see again, based on the zoning and the way that the Taiwanese utilize their ground level facilities, that system really identifies a condition that we as structural engineers would basically identify as a deficiency. And you can also see here what the actual flow throughput on vertical or horizontal transportation, whether it be vehicle or pedestrian, might be. The collapse actually is from the kind of the longitudinal direction of that previous photograph across a street, and of course damaged buildings on the far side of that street. And you can see that there's some buildings here across this internal courtyard. From that failure, you actually have some water lines that are represented here from a recent symposium that was conducted by the Taiwanese, indicating where these water lines are located relative to the collapse. And of course, they were damaged during the earthquake and were repaired immediately following. You can see some sheet piles that have been installed, obviously some pumping of water to try to help with that demolition process, and the process of rerouting these major utility lines. So you can see they're quite tall, typically between 1.5 to 2 meters tall. This is what the space looked like after the demolition was completed. And as you can see, this is approximately 10 to 15 days after the actual collapse, whereby that building had completely blocked this road and damaged buildings across the way. They're finishing the repair of these water lines and, of course, opening the road. That was the big purpose. And you can see that there's actual traffic that's associated with this area, even though you have this major collapse that is responsible for up to 115 deaths. this demolition indicates, here you were seeing that elevated courtyard that actually was just supporting some landscaping, and just behind it was quite a bit of both residential, which is over here, and some manufacturing facility. There's a fully functional machine shop located in this building that when we were there was back up and running what appeared to be fully functional operations. And I'm quite certain that within a day or two after the earthquake, as long as there was power and water, that they were fully functional and continue to be as we left. At the far end of the block, just behind this location again, in the same regional area, we were seeing that telecommunication repairs were ongoing, and this, of course, sometimes takes months to occur. And I'll talk a little bit about other earthquakes and some of their recovery. But here, the Taiwanese are up and running in terms of repair and getting people back online within a couple weeks, if not sooner. So the water distribution failure is a very interesting side note to indicate and to discuss and have us think about things in a resiliency context, because that's really related to how a community responds to the event, not just buildings or just infrastructure. But there were some major water distribution failures throughout the region, and it was dealt with associated with truck mobilization. So there's actually some mobile restoration of water service to the community and the society at large, and then some temporary water distribution lines that were put in place in a very short amount of time. So this is a map showing the major lines within the water distribution system, and you can see these red lines are pretty significant in terms of getting water from one location to the other, and it's primarily bringing water, as you can see, from the mountains down into the populated areas. And some of the failures were actually associated with both large lines and some of these smaller blue lines. And you can see that bringing pipe sections was continuous. This was a photograph that was shared by the Degenkolb team, bringing these pipe sections into an area where you can see that there's some demolition and reconstruction occurring. And as you can see, here we are within, again, 10 days of the event. The traffic is not affected at all by the work that's going on. People are really back fully functional. So this is an overview of one of the major waterline failures, and you can see that they're coming to an area that would be below grade where a water line exists and is functional, and then they brought it above ground and they've started to run across above ground, and it carries along here more than 7 miles, so well more than 10 kilometers down the center of a major thoroughfare, which blocks the actual through traffic into adjacent roads. By the time that we were there, the community had figured out that this was going to happen, and they actually just run to the end of the pipe, which eventually ends and either diverts to the left or goes underground, and then turn a U-turn and then come back to the areas where they want to gain access. There was discussion about a school evaluation retrofit program that was brought on after the Chi-Chi earthquake. Obviously, they had over 400 buildings that were evaluated, and again, 335 were identified as safe, with 1 being damaged, and 75 of these buildings were identified as unsafe, and 18 of those were deemed damaged. One item of note, so this is the building that was damaged. It was deemed to be unsafe, so there was no retrofit applied to this building. Some of that may be related to an overall functionality target, which is, can we use the school if the earthquake damages this building? Well, indeed they can. Again, 10 days after the earthquake, this junior high school was in full function mode, and new buildings that were built after 2009 are in place and functional here. And so resilience is more than just making sure that all buildings survive, but really it's necessary buildings and then how you use them to respond. This is at the same campus where we had some water tanks fail. They didn't fall from above. These actually just tipped over here at their local condition. These are the water source for a lot of buildings throughout Taiwan, and they're incredibly poorly built and poorly anchored, and so they had to deal with these on a large scale. This is a photograph from the top of a roof in an adjacent area, and you can see that there's probably 10 to 50 in this photograph. If you squint, you can see some that are all the way back here, but there are literally thousands of these all over the city, and many of them were repaired and replaced by the time we got there within 10 days. Obviously, a private company is coming out and helping replace these tanks with minimal fanfare. It just happened, and then of course the piping is reconnected and off you go. The hospitals performed very well. This is the Jiun-Wei Medical Center with over 1,200 beds. There was no disruptive damage. It was basically fully functional, and people utilized it as a normal hospital. The throughput at that hospital was controlled outside of the hospital, so the Taiwan response to the earthquake was controlled such that beds were utilized for those that needed them, and the actual services were not clogged unnecessarily. This is a University Medical Center near downtown Tainan that I showed in one of my first slides. It also did not have any disruptive damage and appeared to be fully functional. This is a photograph inside of that medical center, and you can see it's basically of size related to an airport. Really no damage that you could observe anywhere, and even if it was not affecting its use as a hospital as intended. And it seemed like business as usual, again, within 2 weeks of the earthquake occurring. So in comparison to the Chi-Chi earthquake, I have some of the earlier statistics I showed compared to the Chi-Chi earthquake. So you can see magnitude 7.3, 7.7, and here we're talking a magnitude 6.4, so obviously a significantly greater earthquake. Location, obviously close to some development, but really very far from Taipei and Tainan. Still damaged buildings in those areas because it was such a large earthquake. And of course, Tainan had a much closer epicenter with closer relative damage related to what we're seeing there. What's interesting is although there was more widespread damage in the Chi-Chi earthquake, it was very similar to what we saw in Tainan. And of course, you can see for all the same reasons, the same type of systematic layouts and the same type of construction defects. Now, in comparison on a global scale, it's worth looking at the Christchurch earthquake in February 2011. While this is not a direct comparison and in no way says anything about the two different areas related to either the response, the ground shaking, or the types of damage that we saw, it's interesting to look at the response from a societal and resilient standpoint, since that's becoming such a buzzword to talk about how a community can actually respond to damage like we're seeing. So you can see that the main shock at the Christchurch earthquake happened quite a distance from the Central Business District, which is CBD, which was close by this 6.3 aftershock, which is very close to a representative type of Taiwan event, or an event that could be compared to a Taiwan event. So you can see there's pervasive damage related to the URM construction, which was prevalent in Christchurch, and that's all of these URM walls that are peeling away and really causing some disruption to the downtown area within Christchurch. And to that extent, Christchurch responded very differently than they did in Taiwan, and rather than go about business as usual, they're very much protecting people by keeping them out of those areas deemed to be hazardous. And that initially started in this Central Business District that actually grew a little bit and basically eventually kept people away from what was an area where people were trying to really assess in the very early hours after the earthquake, and it turned out for months afterward. And then the response in terms of how to actually get Christchurch proper, which is basically this yellow section, identified in terms of a response and a reconstruction condition. It was a very, very different earthquake, and I'll talk a little bit more about that statistically. I have a photograph here of that view, basically looking towards the center star there. And this photograph is relatively famous from the earthquake. It was taken right immediately following the event, and you can see that quite a bit of rubble hit the ground and it actually caused a little dust cloud. And you can see based on that earlier photograph that I had, very similar in terms of the possible area affected, but you'll see based on statistics a far, far fewer number of buildings. So in Christchurch, obviously, it was a very focused effort to try to understand what buildings were affected and how to recover. And so these statistics speak for themselves. About 5,000 buildings were inspected, and about a quarter of those were red tagged, which meant that people could not use them. And of course, the residential percentages were much, much less. And what we're seeing in Taiwan is that we're really on the order of the residential percentages in terms of red tagging, and this seemed to be the distribution. And so if we're talking about red tagging over this area is significantly larger than the area of investigation in Christchurch, just based on a geographical region basis. And you can see that a far fewer set of buildings were damaged as part of this Taiwan earthquake, and the results really speak for themselves. So the urban population of Christchurch is much, much smaller than Christchurch, about 1/6. The urban area is about a quarter the size of what we see in Tainan, and of course the density is also similarly small. However, the damage that was identified within Christchurch, and remember that red tagging is actually a societal result of the earthquake. It isn't a guaranteed quantified metric that is the same everywhere. It's what people deemed to be completely unsafe and unusable. And it really stopped activities from occurring in Christchurch and was very significant. If you have a 25% condition, then you really can't get back into your buildings and get back to business as usual. The recovery time is really, while it's unfair, it's pretty honest that Christchurch is really not recovered, and we're going to be easily 6 years out here before they even approximate something that's along the lines of recovered. They're a very resilient population, but in terms of getting things back to business back as usual, very much like Katrina, where people have just vacated, and there's really not a draw to get them back into business as usual in downtown Christchurch. In Taiwan, it's safe to say that within less than a month, they're going to be back as business as usual, and people will deal with those repairs that they have to, but the response was much, much different, and it seemed to be a much more resilient society based on either the level of damage or the society's willingness to respond. I put this slide up here. It was a beautiful slide developed by ATC and Bill Holmes. Just to look at timing associated with earthquake was really the focus, is that many earthquakes of magnitude of interest in the U.S. have occurred outside of school hours, and that's one of the things that has always interested us. But I think it's important to also recognize just how many 6-point-something earthquakes have occurred within California and even the United States in general, and consider what our response has been as a society and how we respond to that. South Napa is probably one of the most recent and concurrent type earthquakes in terms of both response and level of damage. And it took us a while. The media really got in the way of that and made it seem like damage was much worse than it was, but it was, again, on the order of what Taiwan saw. And if you were involved at all with recovery there, few people in Napa were very vocal about trying to get people to keep coming to the city, because in general it was 99% functional, and there were obviously a few buildings, but that tended to be the focus. So that's the end of our talk now, and I'm sure that Shiza will take over and run our question and answer period. Thank you.
So hi everyone, thank you very much, Kevin, for your presentation, and thanks to all the speakers. We don't have much time left in the webinar, so I think we have time for one question here, and I'm going to pose a question I received from the audience to Tara. So Tara and Joseph, actually, I'll unmute both of you so that you can hopefully respond. But the question is, were there observed damage to buildings, lifeline systems, and transmission lines associated with ground strains or rotations? It looks like you mentioned a bit about liquefaction, but the question is more about ground strains and rotations.
This is Joseph. I went to a presentation hosted by ENCRE, and it says that the transmission lines damage that was described before mostly are not related to ground deformation. They are always damaged or determined to be damaged by transient motion or peak ground velocity. However, there were two areas of distribution line of the water distribution line that showed a systematic damage pattern. And the water department thinks that those distribution lines may be damaged caused by liquefaction. But there were no ground displacement damage for the transmission lines. Ground displacement damage only occurred at the distribution level. That's what I got from the presentation offered by ENCRE. Tara, do you have any insights?
No, I remember that discussion of those observations. I would only add that, in terms of major infrastructure, buildings and bridges, major public infrastructure, I think the overarching sources of damage were ground failure induced by liquefaction, as we discussed here. I don't recall any ground failure features that manifested into structural damage of infrastructure.
Thank you both. Actually, we have probably time for one more question here as well, and it's the same. It's a question to both of you in addition, and it's about liquefaction and your comment that previous earthquakes hadn't densified the soils, and the person is asking whether or not you guys were able to define and evaluate the critical void ratio of the liquefiable soils to help kind of, that led you to the conclusion that previous earthquakes hadn't densified the soils so that liquefaction was prevented?
This is Joseph. I'll try to answer that question. The answer is no, because at the time of our visit, there was no sampling being done at that time. And I'm pretty sure in the following months, there will be geotechnical investigation for the liquefiable sites. So hopefully at that time, they will be able to identify the critical void ratios. But at the time of our visit, we didn't have that time to make that assessment. The only information we got is that one of the slides I've shown that the repeated liquefaction sites has a SPT blow count vary between 2 and 5. And in Tara's presentation, the liquefiable sites that we did shower velocity measurement of, and usually we pick one site that is inside the liquefaction zone and one site is outside the liquefaction zone to show comparison. And we always find that within the liquefaction sites, once the shower velocity drops below 100, that typically shows there are liquefaction. If you trust the correlation between SPT end value and shower velocity, that corresponds to a blow count about 8 to 10. So we know that in that area, when you have a blow count between or about 8, the liquefaction potential is very high. And the shower velocity profile may be a very simple, cheap, intrusive test that can be used as a screening tool to identify which area that needs detailed geotechnical investigation, which include borings.
Thank you, Joseph. And with that, we're nearing the end. So this is Heidi Tremaine, and on behalf of the Earthquake Engineering Research Institute, we want to thank everyone for joining today's webinar. I also want to make sure I give a great thank you to our speakers. We appreciate the time you all spent to give us such comprehensive presentations and for your willingness to have this video posted and to share your slides later. So for all attendees who will be here, we're going to be posting a recording of this webinar as well as the slides from the presenters at our the ERI Earthquake Clearinghouse site for the Taiwan earthquake. The URL is on the page. And we'll also be offering professional development hours to those who are interested. And we will send you a link to that for all attendees who join the webinar. You'll get an automatic email when the videos are live and when the PDH form that you need to fill out is available, and we'll send that in the next week or so. So once again, thanks to our speakers, and thank you also to all of our collaborators in Taiwan, without whom this would have been impossible. So we look forward to telling you more about some of the future earthquakes as the situation develops in both Ecuador and Japan. Thank you everyone for attending today.